In this section, we're going to talk about the comparison tests. The comparison tests are going to be a very useful tool for us going forward. And what the comparison tests do for us is they allow us to take kind of complicated series, something with maybe where there's tons of terms in it or something that's just kind of complicated to get our heads around. We don't want to use the integral test. We don't want to, maybe it's not exactly a geometric series, but it's close. So we have these complicated series. And then what we're going to do is we're going to compare them to a simpler series that we know a lot about, typically a P series or a geometric series. And the comparison tests actually have two parts. There's two comparison tests. The first is what the book focuses on mostly, which is what I like to think of as the comparison test with the inequality. So the inequality comparison test, or sometimes just called the plain old comparison test. And what it says is that if you have two sequences, say A sub n and B sub n, and A sub n is always less than or equal to B sub n, and it's important here that both terms are non-negative. But if A sub n is smaller than B sub n for all n, then we have some relationship between the convergence of the sum of A sub n and the sum of B sub n. In particular, if the sum of B sub n converges, then the sum of A sub n converges. And that makes sense if you think about it. So imagine that you have a pile of the terms A sub n here and a pile of the terms B sub n here. And the B sub n terms are all bigger than the corresponding terms in the A sub n. When you add up the bigger stuff, you get a bigger sum. That's all that this comparison test is actually saying, right? If you add up terms in two series, and the terms in one of the series are all bigger than the terms in the other series, well, then the sum is also bigger. Okay, that's really the comparison test in a nutshell. So if what this means in the kind of the application and how we're going to use it is that if the sum of B sub n converges, so if the sum of the larger terms is say 5, then the sum of the smaller terms is going to be some number that's less than or equal to 5, and therefore it'll converge. It's not going to go to infinity. Notice that if all the terms are positive, then all the series are going to have positive values. And the reason why that's important is that we're actually ruling out the divergence that we get when we have things like sine of x or alternating series, where you have divergence kind of for silly reasons because it like alternates. It's not divergence to infinity. It's just that it doesn't settle on a particular value. That's ruled out completely if all of the terms that we're adding in the series are positive, because that means that the partial sums are an increasing sequence because we keep adding more and more positive terms. Anyways, that's one of the kind of technical reasons for that inequality. So if the sum of the bigger terms converges, then the sum of the smaller terms converges. That's the first part. The second part of the comparison test is that if the sum of the smaller terms diverges, and remember that we're only talking about diverges to infinity here, then the sum of the larger terms has to diverge as well. Okay, and so that's the comparison test in a nutshell. The way that I like to remember the comparison test is with the following inequality, which is technically incorrect, but still useful, which is its own little niche category of things. But it's basically a mnemonic device. And what it says is that suppose you have these two sequences. So I've just rewritten the first part, A sub n is less than or equal to B sub n for all n, all the terms are positive. Then the sum of the terms A sub n is less than or equal to the sum of the terms B sub n. Okay, that's really what the comparison test says. And you can interpret this one of two ways. If this series is 5, well, then the series has to be less than or equal to 5. And if this left series, the sum of A sub n, the sum of the smaller terms, if that's infinite, then this is bigger and therefore also infinite. So that's really how we interpret this inequality with the comparison test. Okay, and so what I want to do now is talk about some examples where we use this comparison test in some places where it could come up pretty nicely. And so what I want to do is I'm going to give you, in this case, 3 series. And what I want to do is just figure out, do they converge? Do they diverge? Okay, and then we'll move on. There's actually another set of comparison tests that I'm going to talk about at the end of the video. So the first series is we're going to look at the sum of arctan of n over n cubed plus 4. And I'm going to start this series at n equals 1. And what I want to do is I want to think about what can we compare this series to. So what's a series that we know very well that we could compare this to? And so the n cubed plus 4 in the denominator is basically n cubed. So notice that n cubed plus 4 is greater than or equal to n cubed. And that's actually true for all n. Okay, that's true for all. I don't know where that extra line came from there. But that's true for all values n greater than or equal to 1. It's actually true for all n regardless of the value, but in particular, the values that we care about are from 1 to infinity, and that's true for those. Now, what this tells you is that when you take the reciprocal, 1 over n cubed plus 4 is less than or equal to 1 over n cubed because the denominators are larger. So again, for all n, we have the inequality 1 over n cubed plus 4 is less than or equal to 1 over n cubed. Now, also, we can see that if we have arctan of n, that's always going to be less than or equal to, it turns out to be pi over 2, because we know that as n goes to infinity, this function is going to approach pi over 2. We also know that the function f of x equals arctan of x is increasing because its derivative is 1 over x squared plus 1, which is always positive. So we know that this function is always increasing. Maybe we also remember what the graph looks like. But the function is always increasing. It has a bound. Arctan of n is always less than or equal to pi over 2. And therefore, what we can do is we can put these two inequalities together. So I'm looking at this inequality here and this inequality here. And we'll put these together. The way that we do that is we're going to look at arctan of n over n cubed plus 4 is being equal to arctan of n times the quantity 1 over n cubed plus 4. And what I want to do is let me give myself a little bit more room here. Notice that this first term, arctan of n, we said is always less than or equal to pi over 2. So that's all I want to say about that. So arctan of n is less than or equal to pi over 2. And 1 over n cubed plus 4 is less than or equal to 1 over n cubed. That was the other inequality that we got from our work above. And if we put these together, what we end up with is pi over 2 over n cubed. And therefore, when we look at the series, the sum of arctan of n over n cubed plus 4 from n equals 1 to infinity is going to be less than or equal to the sum from 1 to infinity of pi over 2 over n cubed. And of course, pi over 2 is just a constant, so we can bring that out. So we end up with pi over 2 times the series from 1 to infinity of 1 over n cubed. Now, the sum of 1 over n cubed, we know converges as a p series with p equals 3. So this converges. It's a p series with p equals 3. I don't care what it converges to. All we care is that it converges. And since the original series is less than or equal to a convergent series, this tells us we can conclude that the original series that we were looking at, arctan of n over n cubed plus 4, as n goes from 1 to infinity, this also converges. I can't spell. This also converges. Okay, and that's how we're going to use the convergence theorem, the comparison test. We had a series. We showed that it was less than or equal to some constant times a p series, 1 over n cubed. We know that this p series converges. Since this original series is less than that, it also converges. That's the entire argument. That's the comparison test in a nutshell. Okay, so that is the first inequality I wanted to show you, or the first use of the comparison test that I wanted to show you. Let's look at a few more. Let's look at the, I want to determine whether the following series converges or diverges. Let's look at cosine squared of n over e to the n. And What inequality do we know about cosine and sine? Well, we know that cosine and sine of whatever value is always between -1 and 1. So cosine of n is always between -1 and 1. And therefore, when we square it, cosine squared, anything squared is greater than or equal to 0, but cosine squared is less than or equal to 1. So this tells us that the sum of cosine squared over e to the n is less than or equal to 1 over e to the n. In 1 over e to the n, we know converges. It's a geometric series. Its geometric ratio is 1 over e. So this is 1 over e to the n. And therefore, this converges. We actually also know what this series converges to, although it doesn't matter for this problem because all we needed was to show that the original series was bounded by it. And therefore, the original series cosine squared of n over e to the n has to converge. So this converges by use of the comparison test. That's it. It's really the entire argument there. Finally, let's look at e to the 1 over n divided by n as n goes from 1 to infinity. And what I want you to notice is that e to the 1 over n is, we're thinking about, so as n goes from 1 to infinity, we get e square root of e, cube root of e, fourth root of e. This is going to tend to 1 because the exponent tends to 0, and therefore e to the 0 is 1. This entire thing is going to tend to 1. But e to the 1 over n is greater than or equal to 1 for all n. And that turns out to be the relevant inequality for us here. So this is greater than or equal to 1. And therefore, e to the 1 over n divided by n is greater than or equal to 1 divided by n. And since the right series, since this larger series, since this series on the right of the inequality diverges, so since this right series diverges, it's the harmonic series. We've seen in many contexts that this diverges. We've given actually, I think, 3 different arguments that this diverges now. So since this series diverges, so does the larger sum. So does the sum e to the 1 over n over n. Okay, and that's it. That's the comparison test. That's how this gets used. I think I'm going to stop the video for now and break this up into 2 pieces. In the next video, we'll talk about the limit comparison test, which is the second of the comparison tests from this section.